Okay, today we are going to talk about electric flux. Electric flux is a scalar quantity. It is a scalar quantity. We will get to know why it is a scalar quantity. And it is denoted with a symbol phi e, phi suffix e. That is the symbol of electric flux. Now, before we start with electric flux, we will do a brief recapitulation of area vector. We all know that area is a vector quantity. We have done it in our lecture of solid angle. Area is a vector quantity and its direction is given by the outward drawn normal to the surface. So, if this is a surface, the area vector is given, the direction of the area vector is given like this. If this is a surface, direction of the area vector is given like this. Okay, so area is a vector quantity and its direction is along the outward drawn normal to the surface. Now, especially when the surfaces are 3D surfaces, the area vector is the outward drawn normal to the surface, like that of a cube, a sphere, a cylinder. Okay, like when you are having a cube, suppose if you are having a Cartesian coordinates like this and I draw a cube here, then this surface, the area to this surface is in this direction. The area to this surface is in this direction. The area to this surface is in this direction. The area to this surface is in this direction. The area vector, all are area vector. The area to the front surface is outward. The area to the back surface is inside the plane of the paper. Okay, so all is outward normal to the surfaces. Similarly, if I draw a cylinder, then the area vector to this plane surface is in this direction. The area vector to this plane surface is in this direction, and the area vector to the curved surfaces is in this direction. So you can see the area vector is along the outward normal to the surface. Okay, similarly for a sphere. For a sphere, the area vector is outward normal to the surface. And perpendicular to the surface of a sphere always passes through its center. Okay, perpendicular to the surface of a sphere always passes through its center. Okay, now moving on to flux. Electric flux, it is the number of electric lines of force passing perpendicular to the surface. Number of electric lines of force passing perpendicular to the surface. Now suppose you are having a surface like this, and this is the number of electric lines of force passing through the surface perpendicular to the surface. Mind it, what do you mean by the lines of force passing perpendicular to the surface? If this is the surface, then this is the area vector, and this is the electric lines of force, electric field. It's a uniform electric field. Okay, then area vector and the electric field vector are in the same direction, or the area vector is normal to this surface. So the electric field vector should cut the surface normally. The electric field lines should cut the surface normally. Then the number of electric field lines passing normally through the surface is called the electric flux. It's a measure of the electric flux. So here the electric flux phi E is equal to 2. The number of electric lines of force passing normally through the surface. So you can see two lines of force have cut the surface normally. That is along its area vector, because area vector is outward normal to the surface or perpendicular to the surface. So if area is perpendicular to the surface, then this is also perpendicular to the area is perpendicular to the surface, then the electric field lines are also perpendicular to the surface. Okay, so the electric field line should cut the surface normally, then only that will give you a measure of the electric flux. In no other condition it will give you a measure of the electric flux. The electric field line should cut the surface normally, not parallelly. If it is parallelly, then it will come out to be 0, and we will come to that. Okay, now how can the electric flux be increased? I want to increase this phi e, the value of the electric flux. How can I increase that? Of course, if I make this area large, then I can increase the electric flux, phi e. Okay, more number of electric lines of force will pass through the surface. So here you can see all the 4 lines of force have passed through the surface. So electric flux has increased, phi e has increased when A has increased. Okay, now how else can I increase the electric flux? I can increase the electric flux if I keep the surface area same, but I increase the strength of the electric field. What do you mean by increasing the strength of the electric field? Electric field strength increases when the electric lines of force are closely packed, that is, they become more dense. So here you can see if the electric lines of force are closely packed, then electric field has increased. So phi e again is becoming equal to 4. 4 electric lines of force are cutting normally the surface, passing perpendicular to the surface. So phi e is equal to 4, and phi e has increased because electric field strength has increased. So phi e depends upon the area of the surface, and phi e, the flux, electric flux, depends upon the electric field strength. So electric flux depends upon electric field strength, electric flux depends upon the area. So electric flux actually depends upon both, upon the product of this two. But along with this too, electric flux also depends upon the angle between E and A. And how does it depend upon the angle between E and A? Let us see. Suppose you are having this as the area, as the surface, and so the area is in this direction, and suppose the electric field vector is in this direction. Okay, so electric field vector is in this direction, so the angle between them is theta. Fine. Now that component of electric field vector will only contribute to the electric flux which is perpendicular to the surface. That component of electric field, this is the electric field. Now the component of electric field perpendicular to this surface is this. What is this? E cos theta, and this is E sin theta. Now E sin theta is grazing the surface. E sin theta is grazing this surface. Okay, it is not cutting the surface, it is grazing the surface, just touching the surface without cutting the surface. Whereas E cos theta is cutting the surface. So E cos theta will contribute to the electric flux. So it is actually E cos theta into A, or EA cos theta. We know what is EA cos theta, that is nothing but E dot A. And it is a scalar quantity. It is a dot product of two vector quantities, is a scalar quantity. So phi E is a scalar quantity. Okay. Okay. Now phi E, the unit of phi E, unit of electric flux, is given by phi E is EA cos theta. Unit of E is Newton per coulomb. We know unit of A is meter square. So Newton meter square per coulomb is the unit. Now we will do a numerical. Suppose you are having a sphere of radius 4 meter and that contains a charge plus 50 coulomb at its center. So a radius R and it contains a charge plus 50 microcoulomb at its center. Okay, so you are asked to find out the electric flux emanating through the sphere or passing through the sphere. How you are going to do that? Phi E is equal to EA. Now EA, A is the area vector, and area vector to a sphere is the perpendicular to the surface of the sphere, and as I have told you, perpendicular to the surface of a sphere always passes through its center. So this is the area vector is in this direction, and the E is also in this direction because this is the charge, and for a positive charge electric field is outward, radially outward. For a positive charge electric field, positive point charge electric field is radially outward. So radially outward electric field, and the area vector is perpendicular to the surface and perpendicular to a sphere always passes through its center. So electric field vector and area vector both are in the same direction. So EA cos 0 degree. So E and A, what is the area? Total area is 4 pi r square. Okay, cos 0 is 1. So what is E? What is the formula for E? Intensity of electric field at a distance r from a point is 1 by 4 pi epsilon naught Q, say Q by r square into 4 pi r square. 4 pi goes, r square is going, and Q by epsilon naught. Okay, this Q is the net charge enclosed by the spherical surface. Net charge enclosed by the spherical surface. Now you put the value of Q 50 into 10 to the power minus 6, and this is 8.85 times 10 to the power minus 12. You are getting that to be equal to 5.65 into 10 to the power minus 6, 10 to the power 6, Newton meter square per coulomb. Okay, and if the charge, if what would have happened if the charge is negative? If the charge would have been negative, what would have happened if the charge would have been negative? What would have been the answer? The answer, if there is a negative charge, means the electric field, direction of the electric field is inside, it's entering. And there is a condition you have to remember, that if the electric field is entering the surface, then the electric flux is negative. If the electric field is entering the surface, if this is the surface and minus 50 coulomb is at its center, means the electric field is entering the surface. Okay, and if the electric field is entering the surface, electric flux will be negative with the same value, minus 5.65 into 10 to the power 6 Newton meter square per coulomb, but it would be a negative value. When electric field is leaving the surface, electric flux is positive. When electric field is entering the surface, electric flux is negative. Now with this or with considering this case that electric area vector is outward drawn normal to a surface for 3D surfaces, or considering this case that when electric field is entering the surface, then electric flux is negative. When electric field is leaving the surface, electric flux is positive. We can consider either of the two cases, and we will go to a numerical where I take a cylinder is immersed in a uniform electric field with its area parallel to its axis. A cylinder is immersed in a uniform electric field. Okay, so the electric field is passing like this. A cylinder is immersed in a uniform electric field with its axis parallel to the field. You have to calculate the electric flux emanating through the cylinder. The cylinder has, we take small areas dA on both sides. Okay, on the both plane ends. This is plane end 1, this is plane end 2, and this is the curved surface 3. The three surfaces of the cylinder 1, 2 and 3. Okay, 2 plane ends and 1 curved surface. Okay, so for the plane end 1, we are taking a small area element dA whose direction is outward normal to the surface. For the plane end 2, we again take a small element dA whose direction is outward normal to the surface. And for the plane end 3, we take a small element area dA whose direction is outward normal to the surface. Okay. Now, the net electric flux phi1 for the first surface will be E dot dA, that is EdA. What was the direction of E? Can you see the direction of E is in this direction and direction of dA is in this direction. So EdA cos 180 degree, that is minus EdA. D phi 2 is direction of E is in this direction and direction of dA is also in this direction. So EdA cos 0 degree, that is EdA. And for the curved surface, you can see the direction of E is in this direction and direction of dA is in this direction. So the angle between them is 90 degree. So d phi 3 is EdA cos 90, that is 0. So if you sum it up, the total flux is equal to integration of, you can do the integration minus E. E is a constant, the uniform electric field. So I take E outside, E minus EdA plus EdA plus 0. That comes out to be 0. The electric flux, if a cylinder is placed in a uniform electric field, then the electric flux passing through the cylinder is 0. Similarly, we can find it out for a cube. If a cube is placed in a uniform electric field, then this is the direction of the electric field. Then the electric flux passing through the cube is 0. How you can take it? You take this surface to be 1, this is 2, this surface to be 2, the top surface to be 3, the bottom surface to be 4, and 5 and 6 are the front and back surfaces. Okay, so here you take a small area element dA such that dA is in this direction. So E and dA are in opposite direction. You take a small area element dA, E and dA are in the same direction. Here in this case, E is in this direction and dA is perpendicular, so 0. Here in this case, dA is in this direction, outward drawn normal, and E is in this direction, so the angle between them is 90 degree. So they can. So what will be the flux? EdA cos 90, 0. EdA cos 90. This is the direction of E and this is the direction of dA, outward normal. So EdA cos 90 is 0. Here it is EdA cos 180 because E is in this direction, dA is in this direction. So cos 180. E is in this direction, dA is in same direction. EdA cos 0. So these two cancel out. This is plus EdA, this is minus EdA. Flux through this surface and this surface. For the front and back surface, again EdA cos 90. So 0. So this also comes out to be 0. The same way as we have done this. But find out when you are having a sphere, a